Hey guys, good day. You are in ATJ channel. And for today's video, I'll be teaching you an organized way to read steam tables. So I have prepared here one example problem, and we are required here to determine the missing properties and phase descriptions in the following table for water. So I only have here two items. This will be just very brief. I have to make sure that this is brief since the main goal here is for me to demonstrate and show to you how to be more organized in answering these kinds of problems. And I have prepared here a step by step guide which will help you um, have a good grasp as to what's really important and what you should focus on when you talk about steam tables. So we have here two items, and we are required to use theme tables to fill in the blanks for each item. And first thing, the only crucial part of answering exercises related to water properties is the determination of its phase. So, of course, these questions are designed for you to infer or determine what's the phase of the water given these properties. And the rest of the solving process is basically mathematical procedure, which covers interpolation and reading of tabular data. So that's the crucial part. And of course, knowing the fact that we have to know its phase first before doing the certain kind of mathematical procedure. So these are the phases that you have to consider first. So water can be a subcooled liquid based on the properties. It can be saturated liquid. It can be a liquid vapor mixture, a saturated vapor, or a superheated steam. So you can do that, or you can infer or determine which among the states is the water in based on the properties by carefully inspecting the given data and compare it or locate it with respect to the saturated steam table. So essentially, the primary data that I'm going to use in inspecting my data is using the saturated steam table. Okay, so let's start here with item number one. You can see here that we have the known pressure and we have the known value of the X. So X here represents the quality, or this determines the mass fraction or the amount of steam that is present, or the percentage of steam present in the mixture or in the substance. So this is quality. So again, this is the mass fraction of steam. So as you can see here, the value of x is zero point 0.6. So this means that there's a portion of the entire substance that is steam, while the other portion is liquid. So this means that um, we have a mixture that is liquid and vapor. So saturated liquid has a quality value of 0, while saturated vapor has a quality value of 1. So if you have a value of 0, that means it's pure liquid water or pure saturated liquid. But if you have a quality of 1, that means you have a pure saturated steam or saturated vapor. So if the value of the quality is in between 0 and 1, automatically the water is in its liquid vapor mixture phase. So this item here, you can easily identify that, oh, okay, I am given the quality. So this means that automatically this is liquid vapor mixture. And usually, if you're not given this value, you have to still use the saturated steam table in order to check if the 200 kPa and the other thermodynamic property that is given, aside from the quality, is in a saturated liquid, saturated vapor, or a liquid vapor mixture. So for this item, this is just very straightforward. So we have to proceed with the process or procedure in determining the properties for the liquid vapor mixture phase. So I'll proceed here to my guide. for item number 5. So I have here a step-by-step method for reading off steam table data for the liquid vapor mixture. So for this state, you need relevant information for both the properties of water in the saturated liquid and the saturated vapor. So this means that you have to use the saturated steam table and get the saturated liquid data and the saturated vapor data. Liquid vapor mixtures have thermodynamic properties that are average of these two saturated states. So use the available data as your basis for getting the saturated properties, and then you gather the necessary data for saturated liquid, and you gather the necessary data for saturated vapor. So depending on how exact or thorough you are in determining the properties, you need to do interpolation depending on the availability of the data. And based on the quality value or the X value, you obtain the average thermodynamic property values using the equation of this one. So M represents any thermodynamic property. And you can find this equation. This equation is actually obtained, this was derived from the inverse lever arm rule that you can use when you have a graphical form of the steam data or the water properties data. So that will be given, or I can explain it in a different video, but for now we can stick to this formula. So first thing, I'm going to gather important data for saturated liquid. So I'll write here gather important data for saturated liquid. So what I have here is I don't know the temperature and I don't know the internal energy of the system. But of course, I know already that this is a liquid vapor mixture earlier. So I'll write here X is equal to 0.60. This is a liquid vapor mixture. So we are tasked to determine the temperature and the internal energy. So the steam table data that I'll be using for this tutorial is the steam table data from Vaness. So I have here the textbook. Okay. So this is the Introduction to Chemical Engineering Thermodynamics 6. Now, to solve for the unknown A and unknown B, I typically use single linear interpolation method. And typically I use the two-point method. Two-point method, what I mean by this is the two-point method in establishing a line. So the basic algebra that we have learned or you have learned when you are still studying algebra. So the first thing that I'm going to determine is the value for A. So essentially my approach here is when I do the two-point method for getting the unknowns. So my goal is to establish the interpolation solution in a way that only the unknown A is present and the rest are given values. So my usual pattern is I copy this unknown and then minus with the initial value and then over the higher limit minus the lower limit. So let me show you how I do my linear interpolation. There are many linear interpolation apps available, but of course, for starters, I mean, you have to also get a good grasp as to how this is done on a manual or a like on a more step-by-step basis. So, which is why I'm presenting you this solution here in this video. So, what I do is I copy the unknown minus the lower limit and then divide it by the difference of the upper limit or the higher limit minus the lower limit. And since I do that pattern for the temperature data, I also do it for the pressure data. Of course, the pressure data should be used for the other side of the equation, since again, the goal here is to only have one unknown in establishing this two-point method interpolation. So I start with 200 because that is the one that's in parallel with the unknown, minus the lower limit, 198.54, divided by the upper limit, which is 211.45. Oops. And subtract it by 198.54. And then again, you use your calculator. Use calculator using the solver function. So I'm assuming here that you already know the solver function. So I won't be any more demonstrating this one here in the video, although soon I might be adding that one to my playlist. So use the solver function to determine A. You can use any variables. Typically, most students use X for the solver function. Okay, and upon solving it, I did my calculations already in advance. I got the value of A, which is 393.38 Kelvin, which is equivalent to 120.23 degrees Celsius. So we already got our first unknown for this word problem, for this item. Okay, great. So I'll write it here. Oops. So apologies for my, oops, I have some issues in my tablet. Okay, 120.23. All right. So the next thing that we're gonna get is the internal energy data for the saturated liquid. So we are still on the saturated liquid data. Please take note of that. So we're still not done yet. So I'm gonna do the same thing, but this time I'll be solving for B rather. Solve for B. Okay, so I'll do the same thing, but this time the left side of a two-point method equation is the internal energy data for the saturated liquid. I'll just write it here just to emphasize that it's not yet the final answer. Okay, so I'll write the same thing, B minus 503.5 over 512.0 minus 503. So essentially, what I'm doing for A, I also do for B. And again, the right side is the known side. Okay, the given data. So I'll just copy paste this one. Okay, to conserve time. Yeah, writing here in Microsoft OneNote kind of makes things slower, but yeah, it's more authentic. It's more how do you call this? Like really how a student learns. You write it down. Very crude and very I don't know if I can use the word authentic. Okay, so 504.5. So essentially, this is the data, kilojoules per kilogram. This is the saturated liquid internal energy data. Okay, we're still not done yet because we need to get the saturated vapor data. Okay, so I'll go to number two. Okay, saturated vapor data. Again, our phase is a liquid vapor mixture. And upon reviewing our steam table, remember that for this steam table, the saturated vapor data is in this column. And we actually have this data here. So this is around this part, this one. I'll just use my cursor to highlight that part. So we are still gonna use some data over here, but we're just gonna change the third column data. So I'll just copy paste here below, and then just do some edits to save some time. Okay, to make our solution faster. Okay, so I'll be replacing this one. We already know what A is. A is 393.38. And I'll be using the unknown C for this one. Okay. And then our data 2529. So I already have a copy here in my notebook. Yeah. So just for your reference, just for me to show to you. Okay, here around this part. So I'll zoom it in for a bit here. 2529, and then our data here earlier was this. And this is our saturated vapor data. So essentially, it's just easy reading off. It's just that you need a lot of practice in determining or um, getting the hang of reading, tables that have a lot of numbers on it. Yeah. So I'll solve for C. I'll do the same pattern that I did in the previous interpolations that I had. Okay, so I'll just copy 200 minus 198.54. So there are a lot of interpolation apps available, guys. And so you can actually do this part easily. But as a student, I'm still using this approach. And in case I can't or I'm not allowed to use interpolation apps during exams, at least I know the fundamental and a more manual way of doing this. So upon solving this part using the solver function, I got the answer of 2529.2. So this is the uh, internal energy of the saturated vapor phase. But now, this item is a liquid vapor mixture based on our analysis earlier. So, as dictated by our step by step guide, based on the quality value, we obtain the average thermodynamic property values using the equation M average is equal to ML plus X multiplied with the difference of the MV minus ML, where M represents any thermodynamic property. So this means that you can replace M with internal energy, enthalpy, even temperature, or even entropy, as long as you are required to determine the average thermodynamic property. Okay. So for the second item, apologies for typing in the wrong information earlier. I think I did some changes when I did my preparations because the second item, the initial data for the second item, somehow has the same approach as to the first data. So I want to give another item that would help us learn different approaches for different phases of water. So for this one, for item number two, we don't have the value for the temperature. We have the value for the pressure, which is 1000 kPa, and the internal energy data to be 2950 kilojoules per kilogram. Okay, so again, the first thing to do is to determine what's the phase description, and from then on, once you know the phase of the water, we can then proceed with the succeeding steps, like what steam data to use. Do we use saturated steam data, or are we gonna use superheated steam data, or are we gonna get um, data for saturated to get the liquid vapor mixture? So for this one, we have a 1000 kPa. So again, the first thing to do is to use the saturated steam table data to see if the internal energy that we have here is available for this value of pressure. So that's the initial assumption. So do not jump yet to the assumption that, oh, this is superheated. So we need to use the saturated steam data first. Okay. So this is the KPA value. So this is around this value. So we have here 1002.7. So in between 957.36 KPA and 1002.7. So more or less our data is within this range because our we have a 1000 KPA. So it's in between here. Now, the data for the KPA, so unfortunately, this the header is kind of twisted. So I'll just count what column is for the internal energy. So one, two, three, four, five, six, seven, eight, nine. So the seventh column and the ninth column. Okay, so let's go back. Okay, now from the data here, so this is the KPA. So one, two, three, four, five, six, seven. So the data here, it says the internal energy, if it's saturated liquid, is around 762. So near this value. So I'll write it down here. So you're gonna present your solution this way. So for item two, so at a pressure of around 102.7 kPa, which is more or less near 1000 kPa. So of course, you would expect your data to be more or less similar. The saturated, okay, let's just write saturated. The saturated liquid internal energy is around 762. Okay, so 762 kilojoules per kilogram. And the saturated vapor internal energy is, so we have here ninth is on 2581.9. So around 2581.9. Okay. So if your water is saturated liquid, then it should have a value of this 762. If your water is saturated vapor, it should have a value of 2581.9. If your water is liquid vapor mixture, it should have a value in between these two given data. But our internal energy data, based on the given information above, is 2950. So this is more than, or this is significantly greater in value as compared to the highest value for the saturated vapor. So this means that this implies that your U is greater than your internal energy for saturated vapor, implying that your data indicates that the water is in its superheated steam form. All right. So that means we're going to use a superheated steam data. So superheated steam data, it's kind of tricky, yeah, at some point. So you have to be very careful as to how you're going to use it. So there's a lot of like crisscross that is going on here. So I'm just going to teach you how to read this off. So of course I have the pressure data. So I need to check the KPA. So I have a 1000 kPa data. So this is the pressure data 1, 10, 20, 30. So I'll just go over and go to 1000. 1000. Where is it? Okay, not here. Okay, oops. What happened? Okay, there's something wrong with the file, I guess. Okay, apologies. Okay, 5000. See, 3000. Okay, so we're near. Okay, here. All right. Oops. We're still far from. Okay, here 1000. This is the kPa. And we need to know what is our temperature. Okay. So for this one, I don't have uh, the reading for the temperature data, but I know what's the value for the because again the unknown is the temperature. So we need to know where the value of the 2950 is located. So we have a 1000 kPa here, and we need to look for the location of the 2950 here. So this is 2917 and 2957. So more or less, the value of the 2950 is in between 2917 and 2957.9. So essentially, the unknown is here. And so the temperature range that we're gonna investigate is 375 Kelvin and 400 Kelvin. So I know the Kelvin date. I know that it's a Kelvin data because it says here that the temperature that is written in this one is in Kelvin. Oops, sorry. That's in degrees Celsius rather. So the one in parenthesis is in degrees Celsius, and the one that is not in parenthesis is in Kelvin. So we are required for the degrees Celsius. So I'll be using 375 and 400. So for this one, I'll be using, again, interpolation. So I hope I was able to simplify my explanation for that one. So I have 375, and then my temperature for you, my value for you is 2917, and I'll just use letter D, 400. This is degrees Celsius, guys.